So yeah, we were just talking about last time. Last time we talked about optimization with quaternions. And I don't know if you got this out of the video, but I'll post on Piazza too. We basically a couple of years ago in the lab wrote a paper called Planning with Attitude, which is basically just a nice little conference paper that I call like kind of Lie groups for dummies. That's sort of doing our version of the simple ways to do quaternion optimization stuff. And all the stuff I taught you in class is just in that paper, kind of in a nice, clean, short little, write-up. So I highly recommend checking that out if you want to have a nice reference for this stuff. And I'll post it. Okay. Let's see. So today what we're going to do is just take that stuff and actually do control with it. So first thing we're going to do is kind of go through how to do LQR with quaternions. And there's a few little tips and tricks in there that make this, it works extremely well, basically, if you do it this way. It doesn't work super, super well if you naively do this with Euler angles. So this is a way better way to do things. And then we're going to take that and apply it to the 3D quadrotor. So we did a little while ago when we did MPC, we did the 2D planar quadrotor. So now we're going to kind of beef that up and do the full 3D version. We do this on hardware. It works super, super well. You can do kind of wildly large angle attitude, recovery stuff, and it still works great. And I'll show you maybe some videos of that at the end. And I'll show you how to do those dynamics and all that good stuff. Okay, so any questions before we get started? All right. That's a sort of whole other conversation. So you can, the sort of Lie algebra thing is, these are submanifolds, right? So if you think about quaternions, the space of quaternions embedded in R4, is that a convex set? Why not? That's exactly right. So the space of 3D rotations, like the set of 3D rotations, is not a convex set, right? So in quaternion land, it's a spherical shell with a hollow interior. And obviously, to draw the line, it's not contained. So that is not convex. Same thing with rotation matrices, actually. It turns out they're basically geometrically the same. And so sort of this idea of a sphere. But they do admit clean convex relaxations that are tight in a lot of cases. So basically, which we're going to talk about later in the class, actually. So that spherical shell is non-convex. If you include the interior, though, and it's a ball, that ball is a convex set, right? So it turns out a bunch of the operations you want to do on quaternions, if you just relax that unit norm constraint into a ball, often you end up, depending on the objective function, you can end up pushed up to the boundary of the set. So for example, if you have a linear objective, right? Like basically the answer to that is go in the gradient of the minus gradient until you hit something. And if that's the flavor of the problem, then you're always going to end up on the boundary, in which case you can solve a convex problem, a relaxed convex problem, and guarantee that you're going to get the exact answer to the original problem. That's called a convex relaxation. It turns out these attitude things actually admit tight convex relaxations in a lot of cases. One of those cases, by the way, is Waba's problem. So Waba's problem, it turns out, we can talk about this offline, but that problem is non-convex. But if you play some games, you can relax it into a convex problem that is tight, meaning the relaxation is exact always. And you can show that pretty easily. So offline conversation, it's subtle is the answer, but you can do some stuff there. Sorry, I'm easily distracted. Okay, here we go. So LQR with quaternions. Okay, so back to what somebody asked, I think you just asked a little bit ago. The problem with, so we talked about sort of this rank deficiency problem. If you're looking at a linear system like AX plus BU, another sort of version of that rank deficiency story is that the system in 4D is always uncontrollable. So like if you try to do LQR on that 4x4 system, it will never converge. Like Riccati will not converge because it's an uncontrollable linear system, because by definition, you can't control in the length direction, right? So that's also kind of part of the story, right? Basically, all the stuff breaks and you have to do some tricks. So naively linearizing a system with a quaternion And I'll show you this in the code in a bit. You have a quaternion state, you linearize. This will give you an uncontrollable linear system. So like if you go try to solve for the infinite horizon LQR gain, like if you call it DLQR, it will barf and tell you it's uncontrollable, right? Okay, so what we're going to do is use the tricks from last time, the attitude Jacobian tricks, to sort of get this into the right sort of lower dimensional system that actually works.
So they said uncontrollable means you can't, the counting equations you can't solve for K.
Yeah, so literally the classical linear systems definition of controllability, right? Where you have this controllability matrix, if it's LTI, and it's like, you know, sort of B, A, B, A squared, B, blah, blah, blah. That controllability matrix will be rank deficient. The resulting linear system is uncontrollable. And as a result, the Riccati recursion, if you go and try to do this, will diverge. It will not converge to a steady state. So normally for an LTI system, right, if it's controllable, that Riccati thing will converge to steady state P's as you kind of iterate. If it's uncontrollable, this is a fun one. Why does that thing diverge if it's uncontrollable? Think about what the cost looks like and what that integral or sum looks like. So with the cost function,
I guess I'm up with this vanish, I guess.
so what happens with that is over time, if the system's controllable, the LQR controller is going to drive it to the origin. So it's going to drive the cost function to 0. So the tail is 0. And so that thing, even though you're integrating for infinite time, the integral under the curve is finite because the error converges to 0, right? If you're uncontrollable, you can't drive the error to 0. And so the cost never goes to 0. And so if you integrate for infinite time, it blows up. It doesn't converge to a constant value. So that's for, right, infinite horizon LQR, right? So that Riccati equation diverges now because the cost doesn't go to 0. So there's always area under the curve. So as you go out to the right to infinity, as t goes to infinity, it's infinite. Does that make sense, everybody? Yeah, that is what controllability is about. It's about the fact that you can drive the error to 0 so that the infinite horizon cost to go goes to some finite value, right? Okay, cool. So we apply quaternion tricks here. To make this all work. Okay, so here's the recipe. So we're going to assume we're given a reference. So this works for time varying or time invariant LQR. And we're going to kind of look at both of these. So we're going to say we have some reference X bars. The bars are the references we're trying to track for a discrete time system. We're going to sort of do the standard stuff where we do the Taylor approximation. So this is, I guess, this should be approx. We're going to linearize it. So this is x bar k plus delta xk, u bar k plus delta uk. And now we're going to take the first order Taylor expansion of this whole thing, and we're going to get, it's weird and annoying, x bar u bar plus a delta x b delta u. And these guys, so first thing to note is this term we can just eliminate because it's x bar k plus 1 equals that f of x bar u bar by definition. And so now we're just going to look at the deltas. And a, as we all know, is partial f partial x, and b is partial f partial u. So now we're going to basically go in and do our tricks on the a and the b with the attitude Jacobian and kind of proceed as usual. So what we're going to do, we're going to kind of build up, we're going to do a quadrotor. So what I'm first going to do is kind of show you what this looks like for something like a rigid body system. So the state is not just the quaternion, it has other stuff in it. So typically for something like a quadrotor, well, I'll show you what the state vector looks like and what we're going to use it. So if you kind of get into this stuff and you use various simulators or rigid body dynamics toolboxes, they have conventions typically for how they stack up the state vector. And I'll show you the conventions that we typically use. Be careful because you might find other conventions, so you can't just plug and chug on this stuff. But here's what we're going to use. So for the quaternion part of the state, we're going to apply the attitude Jacobian. To convert delta Q to this three-dimensional axis angle phi thing, right? Which is an R3. Cool. And so typically our state vector for a quaternion, for like, I mean, for almost like any single rigid body system, which includes quadrotors, airplanes, various kinds of drones, underwater vehicles, a lot of the sort of standard quadruped MPC controllers like the MIT Cheetah controller also use a single rigid body model. So this really shows up a lot for a lot of different systems. That's kind of pervasive. So that's kind of why this is a good thing. Oh, by the way, we actually just had a paper accepted that basically just did these tricks for quadruped sort of standard single rigid body quadruped controller. So I guess it's still a thing worth checking out. So we're gonna stack it as follows. So we have a position, we have our quaternion next, and we all know, right, by convention, that's the body to inertial frame, body to world frame rotation. Then depending on the system, like, so if it's a big robot like a quadruped or a humanoid, you're also going to have joint angles. Often people use Q for joint angles, which is annoying. We're going to use theta for joint angles because we're using Q for quaternion. And then you've got your velocity stuff. So that'll be your like position derivatives, omega, your angular velocity, and then your joint angle derivatives, theta dot. So this is a typical state vector. And if you just kind of stack it up this way, this is the convention we're going to use. That's a pretty common one. I think this is the same one that rigidbodydynamics.jl uses. This will be kind of the first three elements of your state. This will be the next four elements of your state. And then this will be kind of, 8 to n, whatever. And then you get the idea. You can kind of figure the rest out. So we know about the attitude Jacobian that's acting on the Q part of this guy. So what we're going to do is kind of just set up one big matrix that does the attitude Jacobian stuff on the quaternion, and then just identity maps everything else through and leaves it alone. So our delta x, so now the sort of like reduced state, this like state with the 3D attitude parameterization, we're going to write that down. And so basically we're going to have in here like just regular delta x, sort of 1, 2, 3, the position stuff. And I guess it'll be k plus 1. Then we're going to have our phi k plus 1, our 3D attitude error state. Then we're going to have the rest. So this would be delta x sort of 8 to the end. So we're going to call this thing with the sort of attitude error state, we're going to call this delta x tilde k plus 1. And so to get this to work out, we're going to just introduce these matrices that have identity blocks for all the sort of regular stuff, and then an attitude Jacobian. So this is going to be g of q bar k plus 1. And this whole thing's going to get transposed. So this is identities everywhere else, zeros right off the diagonal. So this whole thing's transposed. Then we're going to hit the A matrix, right? Our normal A matrix. If we just use forward diff or just diff it like it's a vector, that's going to be in here. So what this is doing, right, is transforming the output from a quaternion delta to this phi thing. Then we're going to transform the input on the other side. So same deal, identity, attitude Jacobian. This time the attitude Jacobian is at q bar k. It's evaluated on the input, right? And then identity stuff, zeros everywhere else. That's it. And then this thing on the other side, right, is going to have the input to this is the delta k. So this is 1 to 3. This is phi k. And then this is delta x, sort of 8 to the end. Sorry for the Cool. So that makes sense. So we're basically squashing the A matrix with attitude Jacobians just at the quaternion part. You're evaluating the attitude Jacobian at the input, the reference input on the right, and the reference output on the left. You just squash it both ways. And now it's transforming the inputs and outputs from some weird 4D delta Q thing into this nice 3D error state phi, right? Okay, so we're going to call these sort of bigger Jacobians just for sort of notational convenience, where we've sort of put the attitude Jacobian in the middle there with a bunch of identity blocks. We're going to call this capital E for sort of error state mapping or something like that. So this is E of x bar k plus 1. This is E of x bar k. So you just kind of hit the inputs and outputs. And then what about the B? Yeah, did you have a question?
Is one of those transpose, like, is your?
Yeah. So the first one's transpose. There's a transpose up there.
Yeah, so is the E, like, is that whole thing E of x k plus 1 transpose?
Yeah. So it's transposed when you hit it on the left. It's sort of regular on the right. That makes sense?
Yeah.
Cool. I mean, that's kind of usually how matrices like transform, right? They're sort of the covariant or contravariant. You're basically doing a coordinate transformation on both sides, on the input and the output. Okay, what about the B matrix? What do we think there? How's this going to look for the B matrix? What's the input of the B matrix? The controls, right? So do we need an attitude Jacobian thing on the right for the controls? No, right? How about on the left side? What's the output of the B matrix? State stuff, right? So do I need it on the left? Yeah. So the B matrix gets an E transpose on the left, nothing on the right, because the right's the controls. So this, so then yeah, the B part is just going to look like E evaluated at the output, x bar k plus 1, transposed times BK, and then you got your delta UK there. That makes sense, everybody? Because that's the output, right? The output's an error state at time k plus 1. So you're going to sort of evaluate this at the reference at time k plus 1, right? Basically, yeah, just think about inputs and outputs. If the input's at time k, the reference is at time k. If the output's time k plus 1, it's time k plus 1. You're transforming inputs and outputs. So just think about what's going in, what's coming out, and what you need to kind of transform on either end. And the input side, you just slap it on. The output side, it gets transposed. But it's, yeah, you basically, the overall message is just take derivatives like normal. If there's a quaternion in there, think about what you're linearizing with respect to, or what the inputs and outputs are, and just hit it on either side with the appropriate attitude Jacobian, evaluated at the appropriate kind of linearization point, right? Reference point or whatever that you linearized around. Cool, everybody good with this? Okay, so yeah, you can basically do this anywhere. So anytime you have a quaternion in anything, and you want to take a Jacobian, gradient, Hessian, whatever, you basically just do this. Just like do it like you normally would, and then wherever there's a quaternion, slap on an attitude Jacobian. Okay, so now that we've done this, now we have this like reduced system. So we're going to use the tildes for like reduced stuff, right? So we've got X tilde for like reduced error state, whatever. And we're going to similarly call the A's and the B's with these attitude Jacobian things, A tilde, B tilde. So in here, I guess we'll call those reduced. So once we have these, so these, right, we've dropped the dimension, which is useful. So we've got A tilde K, B tilde K. And these, right, just to belabor it and make sure it's super clear, this guy is going to look like E evaluated at x bar k plus 1 on the left with a transpose, A, and then E on the right with x bar k. And then B, you just have the E on the left. So once we do this, once we have the tilde matrices, we just do LQR like normal. And you don't have to do anything else weird, at least for this part. Similarly, right, you just do MPC as usual. Nothing crazy after that. Okay, so then though, the subtlety is, so we get the K matrix out of this as usual. The subtlety now is what do we plug into the K matrix, right? So the K matrix now maps from this reduced state to a delta U. So we've got to plug in the correct like reduced or error state into the controller now. And so now we got to think about how to do that. So when we run the controller, we have to calculate that delta x tilde thing before we multiply by k. And so that's going to look like this. So given an xk, we're going to compute this delta x tilde k. Normally, when we would compute a delta x in like an LQR thing, we would just subtract off the reference, right? So you're mostly still going to do that, except where the quaternion is concerned, we're going to do a quaternion multiplication thing to get an error state, right? So basically, most of this is going to look like, you know, subtraction. So like x minus x bar. But where the quaternion state shows up, we're going to have this mapping phi from a quaternion to a 3-parameter error. And inside there, we're gonna actually multiply the quaternion by the reference and sort of do a sort of on the group error calculation. So we're going to calculate the error quaternion that rotates you from where you are to the reference, basically. So this is going to look like for us L of Q bar K transpose QK. So that's basically doing like a Q bar transpose Q, which is finding you the rotation from the kind of current body frame to the reference, right? And I'll write that out in some more detail if you want. And then the rest, yeah, we just subtract. So that one little trick of like treating the quaternion like this makes a massive difference in the performance of the controller. And technically speaking, this is now a nonlinear controller, right? Because we're actually doing this nonlinear quaternion operation and this like 3-parameter mapping thing when we compute the error state. So now that's all nonlinear, actually. All the quaternion math that we're doing before we plug it into the K is nonlinear. So officially, this is a nonlinear controller. And just as a note, right, we can actually use any 3-parameter phi representation we like. You could, if you were sort of a masochist, you could use Euler angles. I don't recommend. But other good choices would be axis angle vectors, which we talked about, or Gibbs vectors, modified Rodriguez parameters, kind of take your pick, right? Those are all perfectly fine choices. Yeah.
Controllable. Because it can be the A tildes and B tildes will be.
Yeah. So, I mean, okay, to be clear, right, the original A's and B's are not controllable in this kind of, you know, quaternion state. They will never be. Because at the end of the day, it's really a 3-DOF dynamics under the hood, right? So those A's and B's will never be. But if the system is really controllable, this reduced system will be controllable, right? So the reduced system is the one to check controllability on, basically, in this kind of context. If you're trying to linearize and look at the linearized local dynamics, that's the system you want to work with, not the sort of quaternion stuff. So use the quaternion stuff for your simulations, but don't use it for any of these kind of LQR MPC type control calculations, basically. And you have the recipe to go back and forth. Okay, so and then yeah, so you do this, you plug it into the K, and then you get sort of our actual U that we're going to apply to the system is the U bar reference minus K times this delta X tilde that we've calculated like this. Okay, so and then just to sort of make sure it's super clear, because this is maybe a little subtle, like how I got that L transpose Q thing in there to compute this error rotation. Let me just write that out in some detail for you. So error slash delta rotation. So this is, again, one of those things where, unfortunately, life is hard and there are like infinite conventions you can choose here, and you'll see a bunch of different conventions if you read people's code or read other papers. So we're going to pick one here that I think makes sense, but you could do this like 5 or 6 different ways, and you'll probably see them all out there in the wild. So just be careful. So yeah, many possible conventions. So what we're going to do, and that those conventions just come down to choosing frames to represent stuff in, basically, and like orderings, right? So we're going to write it as the rotation. We're going to represent the error rotation as the rotation from the body frame to the desired reference sort of frame, if that makes sense, right? That's how we're going to represent it. That kind of basically corresponds to this error state being in the body frame, which is usually what we want to do in robotics applications, aerospace applications, where we're, have a controller on the vehicle that's using sensors mounted to the body of the vehicle, right? That's like pretty much always going to be our choice. We're going to try to put everything in the body frame as much as possible in here, because it's sort of the natural choice for this kind of stuff. So we will write it as the rotation from body frame, which we'll use capital B as we have been doing, to the sort of reference or desired body frame, which we'll use capital R for in our little frame notations, right? So we had B for body and N for world inertial Newtonian frame before. Now we're going to add this R frame to the mix, right? So what we're talking about specifically is, so here's what we want to have, right? So the reference attitude is this guy from B to N frame, right? That's our convention. We make our attitude the rotation from body to inertial frame. And so to get there, we're going to have this kind of a series. Okay, so this is going to look like we have our rotation from the reference or desired frame to the end frame, and then the rotation from the body frame to that reference frame, right? So this is going to be, if I like kind of label this stuff, this is the actual Q. This is where we're actually at, right? This is the reference Q, the Q bar that we'd like to be at. And then this guy all the way on the right is the delta Q. So that's our error, right? And this is in rotation matrix notation, like it exactly maps over in Quaternions. You just use, daggers instead of transposes, Quaternion multiplies instead of matrix multiplies, et cetera. So if I kind of just plug and chug here and move this around, I'm going to get Q from R to N inverse Q from B to N equals Q from B to R, or equivalently down here, this is delta Q equals Q bar transpose times Q. So that's kind of what this is all saying is, if you have some state estimator, Kalman filter, whatever, that's spitting out your actual attitude Q, and you have your reference desired attitude Q bar, and you want to compute the error rotation, this delta Q, that's how you do it. You left multiply by the transpose of your reference on your actual attitude. So that's the Quaternion equivalent of subtracting the reference. And like I said, there's many, many conventions. You could have this on the left or the right or whatever, and those correspond to which frame you're going to represent the error in. We're always going to choose to represent the errors in the body frame, because that's nice for doing control. Okay, any questions about that? It's a little weird, but that's all it is, right? It's just making a choice, arbitrary choice of convention. Yeah. Yes, the B to R. Yeah, I'm sorry if that's confusing, but yeah, makes sense? Okay, cool. All right, so we're good on that. Again, arbitrary choice, you might see it different. And then, yeah, in Quaternion land, to be super explicit about it, you're going to do it like this. Delta Q equals Q bar dagger times Q, right? It's the exact same thing, just written in Quaternion notation. And then using our matrix tricks, I'm going to write that as L of Q bar transpose times Q, right? Because remember, it's a left multiply by the dagger. So that's equivalent to our L matrix transposed. Easy enough. And so that's how we're going to write it down in the code, basically. And then I take that error quaternion, that delta Q, and I use this, sort of standard kind of mapping. I use a axis angle, Gibbs vector, whatever you want. Take your pick to get the 3D vector phi out of it. Okay, questions about that? Everyone cool with that? Cool. All right, so now what I'm going to do, we're going to do the quadrotor. So I'm going to write you down 3D quadrotor dynamics and just talk through it a little bit, because who's seen these before? Like dynamics for a quadrotor written out or done it before? A couple people. Yeah, so I mean, this is a little bit, tangential. Like I'm not going to ask you to derive this stuff or really, know it in super fine detail, but I think it's worth seeing it and talking through it a little bit before we do it. For those who have not seen it before, this is the standard quadrotor model that's like floating around in like all your kind of Pixhawk, drone stuff. This is what they use. So worth seeing it once in your life, I think. So the gist is we're gonna have a body sort of center of mass, and then we're gonna have 4 propellers, and that was weird. Kind of coming off like this. And these lengths we're going to call L. And let's see, we're going to have, this thing's going to have a mass M and inertia J. And then each propeller is going to have a force F sub I. We'll use sub I for propeller I. And then a torque kind of in the standard, right-hand rule kind of sense. Tau I. Make sense? So propellers have forces and torques. Note that there's no aerodynamics in here whatsoever. We're basically modeling this as a rigid body with thrusters attached to it. So we're not thinking about really in any real detail the aerodynamics. So if you're near a wall, if you're near another quadrotor and you're catching its prop wash, if there's wind, none of that's captured here, right? So this is like kind of in some sense, a pretty simplistic model, but it turns out it works really well. And as is common, right? You can linearize this thing and do really well. And the feedback, the online feedback is going to mop up a lot of the model errors in here. And that's why we can get away with this for these kind of control applications. And then just to kind of show you how this works. So the forces, so with propellers, if you've ever done any airplane stuff or helicopter stuff, propellers spin around, right? And basically one way to think about it is a wing. So wings have lift and drag. If I spin that wing around, it's going to have lift, which is the thrust. And then it's also going to have drag, which results in a torque. All right. So that's kind of, and those, if you go look up a propeller, so like a lot of hobby drone kind of stuff, you can go look online. People do wind tunnel testing on these things and come up with these coefficients. They're called prop coefficients. And there's a thrust coefficient, KT. So for us, we're going to, yeah.
This is assuming, I guess, like a massless propeller, right? Because you're not worried about the movement of inertia.
Yeah, we're not going to model it here because it's sort of in the noise, but you could for sure. If you wanted to build a really high fidelity model, yes. Frankly, there's like aerodynamic terms that matter more than that usually, but you're 100% right. There are definitely like gyroscopic effects from the rotating propellers. But typically, yeah, this is the model. So you'll have like, if your motor is, if you're putting a current in the motor, or we're going to kind of abstract this a little bit, but like whatever your motor torque is, or whatever is going to get mapped into a thrust via a thrust coefficient, and then a torque from a torque or moment coefficient. And these are properties of a given propeller that you can characterize through some testing. And so our U vector, right, is in R4. It's a 4D thing. So basically, roughly speaking, your motor commands are going to get mapped into these forces and torques through some prop coefficients. The linear model is pretty good for prop coefficients, but like everything else, it's an approximation. But that's kind of the standard aero modeling thing. There are weirder effects, though, for sure, that depend. So the first thing to note, right, that's valid at hover. As soon as you start moving, you have some ambient flow that's sort of going over the prop, and it's not in still air anymore. So that model starts to break down. So if you fly really fast, the ambient sort of flow field dramatically affects what the prop does, and then these things start to break down, these linear coefficients. But near hover, this is the valid model.
You just like adding terms to this to make it better. Like,
Yeah. So yeah, basically what ends up happening is the standard thing for this kind of model is basically these prop coefficients are more generally called arrow coefficients, and wings have similar things, right? You have similar like lift and drag coefficient. These are basically the propeller version of lift and drag coefficients. And if you know anything about that stuff, it's dependent on angle of attack and all these other things. And in general, if you wanted to make a really high fidelity model, you'd go do a bunch of like either in the wild testing or wind tunnel testing and measure these things and make it and tabulate them basically, and make a standard thing to do is make a lookup table of these coefficients as a function of speed, Reynolds number, whatever, and then kind of interpolate it into the lookup table in your model, so that you can make these kind of semi-empirical aerodynamic models with just tables of these coefficients that you can fit empirically. Yeah, I've done this before. This is yeah, I've done wind tunnel testing. It's an interesting experience. Okay, cool. So that's that. And again, this stuff works really well up into the point where you're doing like crazy aerobatics, where those things start to matter a lot, right? Okay, so the state vector for the quadrotor is kind of what we wrote minus the joint angles, obviously. So we're going to have a position vector in the world frame, which is obviously, you know, R3. We're going to have our quaternion, as always, from body to inertial, which is in H. I don't know if I talked about this. So that's sort of blackboard bold H for Hamilton, who invented quaternions. So that's like the sort of, I don't know, notation for that. Then we're going to have our velocity. And this is a critical design choice here, actually, that you'll see different in different sort of models and controllers. We're going to choose to put the linear velocity, the translational velocity, in the body frame, as opposed to in the world frame. This actually turns out makes a huge difference. Has anyone seen this before? Anyone can tell me why I might do that? So normally, if I'm doing F equals ma, I'm putting that velocity in the inertial frame, right, in the world frame, because that's where Newton's laws kind of work out, and et cetera. But I'm going to choose to put in the body frame. Anyone have any thoughts on that? Anyone seen this before in other like maybe drone applications or whatever? Well, the IMU is giving you omega and acceleration, but you're right, they're in the body frame, and that's kind of getting at it. Essentially, as before, like I kept harping on this, at every possible turn, we're going to choose to put stuff in the body frame, because that's kind of where the controller lives. There's kind of some deeper group theory kind of reasons for this, though. If I put the velocities in the body frame, turns out that's SE3, which is the Lie group of rigid body motions, translations, and rotations. And it turns out velocity in the body frame sort of obeys those group transformations, whereas velocity in the inertial frame doesn't. There's some fancy math there, but the simple, straightforward reasoning here is when I do it this way, now my errors are in the body frame, which is nice, because when I linearize this thing, remember, I'm linearizing everything. So if my error state's in the body frame, that's the same frame my actuators are in, bolted to the quadrotor. And when I linearize now, there's no extra coordinate transformation in there from body to inertial. Like I've done that outside the control law in my error state calculation. So essentially, putting the errors all in the body frame means they're always lined up with their actuators. And the linearization actually works over a way broader range of attitudes. If I chose VN instead here, now my error's in the world frame. And what that means is if I'm like yawed over 90 degrees, my actuators are like not in the same frame as my error anymore. And you'll actually break the controller at relatively modest yaw angles and stuff like that now, whereas this is good kind of for arbitrary yaw angles, which is cool. So there's kind of subtlety in choosing these frames but the upshot is if you do it this way, basically the message is put everything in the body frame as often as possible, and it works better. And then, yeah, obviously the angular velocity in the body frame as well. Like to your point, that's where the IMU is, right? Our errors are, everything's measured in the body frame, and the actuators are bolted to the body frame. So you'll want it in the body frame. And this guy is R3. Cool. So just to make sure we're all clear, position, attitude, linear velocity, and to be really clear, in the B frame, which is maybe a little bit not typical, and then angular velocity, which is kind of always in the B frame, right? Because Euler's equation. Okay, so that's the whole thing. And there's one so now we're going to kind of do is write out some kinematic stuff, because there's some subtlety because I made some of these frame choices in a maybe slightly strange way. So in particular, the mapping between R dot and V is no longer R dot equals V because they're in different frames now. So I've got a rotation in there, right? So R dot in the end frame is going to be V in the end frame, which is Q times V in the body frame. So that's what my sort of velocity to position kinematics look like. I've got my Quaternion kinematics, which we already know, which is just 1/2 Q times omega hat, which is 1/2 L of Q H omega. And this is all body frame, right? And this is for us now also attitude Jacobian times omega B, now that we define that thing. Okay. And that's so that's all good. We kind of know that. Now what we have to do is write down the dynamics, the F equals MA stuff in the body frame, because we've got V in the body frame now. So that's a little subtle. So we'll do that real quick. Translation dynamics. So we've got F equals MA. So that's M V dot in the N frame equals F in the N frame. So this is the total force, obviously in the N frame. And then this is the acceleration in the world frame. And to make this work for us, because we've defined the state vector with V in the body frame, we're going to have to rewrite this in the body frame now. So that's what we're going to do now. So this is easy. It's just kind of chain rule and stuff we already know. So we've got V in the end frame equals Q times V in the body frame. And now I just need to diff this with respect to time. So I want V dot in the end frame, and that's going to be Q dot times V in the body frame plus Q times V dot in the body frame. And we know that Q dot from the other day is equal to Q times omega hat. So that sort of tells me now this thing is Q omega hat V in the body frame plus Q times V in the body frame dot. So that's the whole thing. And now what I'm going to do is just kind of rotate that whole equation. So I'm going to basically multiply the whole thing by Q transpose. And now that's going to give me, so that Q transpose is going to eliminate that Q in front of V dot. And now I'm going to get the equation in terms of V dot in the body frame, right? So now this whole thing looks like V dot in the body frame equals Q transpose times V dot in the end frame minus omega cross V in the body frame. So essentially what this is telling you is I can basically take F equals MA and just rotate A into the body frame, but then I have to tack on this extra omega cross term, which is coming from the rotating frame stuff, right? So that's kind of it. This is really just rotate into the body frame. And then this is sort of this extra term from the rotating frame, which is kind of what we've seen before, right? This like omega, you pick up this like omega cross term, typically from this kinematic transport thing or whatever. And now if I kind of like just put that all together, I'm going to get V dot in the body frame equals 1 over M times F in the body frame. So I basically just rotate F equals MA into the body frame, right? And then I tack on the extra term, omega B cross V B. Now I've got it all in the body frame, right? Okay, so then to be clear, right, we said the actuators are in the body frame, so that makes that easy, but gravity's not. So the full F in the body frame equals, we've got to rotate the gravity vector. So that'll look like 0, 0, kind of minus mg, right, in the world frame, but I've got to rotate it into the body frame. And then the actuator stuff is nice. So that looks like we have this kind of input Jacobian thing, like that's mostly zeros. But I'm going to have the thrust coefficient from the propeller down here. And that's my multiplying my u's. So u1, u2, u3, u4. Basically, all the thrust vectors point up in the body frame. They all point in the body Z frame. So that's easy. I'm just adding up the thrusts from all four props. And then I have to rotate the gravity vector into the body frame and tack that on. So that's the total force. So that's everything going to be on the body frame. Everyone cool with that? And now the last part is the rotation dynamics, which we've kind of already seen and know, which is just Euler's equation. And the only kind of thing we got to do there is figure out the torque. So this, we've already seen this. It's J omega dot in the body frame plus omega cross J omega, all in the body frame, equals the torque and the total torque in the body frame. And this thing is called Euler's equation, right? We've hopefully seen this before. And then this J thing is the inertia matrix. All in the body frame. Everything's in the body frame. Yeah. So fun one. Has anyone like had to measure an inertia matrix before on hardware? What would you do?
Just like spin it and see.
Yeah. So you can get it from a CAD model. That's like a pretty standard thing to do. But if you actually need to measure it, there's a fun little thing that if anyone wants to check this out, I've done this before. It's surprisingly easy. You can make this rig called a bifilar pendulum. There's actually like a write-up on MathWorks somewhere about it, which you basically take your thing, hang it from two parallel strings from like the ceiling, and you twist it a little bit and let it go, and it'll oscillate back and forth. And it turns out that period of oscillation is directly related to the inertia about that axis and the spacing and length of the pendulum strings. So you get a tape measure the pendulum strings, get a stopwatch, measure it like, measure like 10 wiggles or whatever to get the rotation period. And then you can really easily back out the inertia. So then you kind of just repeat that experiment about a few different axes and you get the whole matrix pretty quickly. Turns out surprisingly accurate too. I don't know. Fun fact, if you ever have to measure it, that's a good way to do it. So that's the dynamics. And then the torques look like, so it's like R cross F, right, is torque. And the R here is that L, that propeller distance from the center of mass. So we're going to get like an L times the thrust coefficient times like U2 minus U4, the propellers that are opposite sides, right? So that's from the thrust. Same thing down here. And this is just convention how I'm numbering the propellers. But basically, you've got sort of opposing thrust on two sides is going to give you a torque just like R cross F, and that's what that's from. And then you're also going to get a torque in the Z-axis from the prop torque, from those torque coefficients. And that's actually what gives you yaw control authority on a quadrotor, is that prop torque. And the subtle thing is you need those props to spin in alternating directions for you to be able to like control the yaw and sort of cancel out those prop torques so it's not spinning all the time. So we're going to have alternating signs in here. And this, this is sort of a detail that might vary between quadrotors and models. And, you should check the conventions, but we're kind of just assuming it's right-handed, positive, and like alternating as you go around kind of thing. Okay, so that's the full up 3D quadrotor dynamics. This is the standard model, like basically used in any kind of quadrotor sim and used in pretty much any kind of quadrotor controller, unless you're doing something really crazy, next level, like crazy racing or aerobatic stuff. In those cases, people do more detailed prop modeling, more detailed aerodynamic modeling, and the latest stuff from like kind of folks doing drone racing and stuff like that. They're now using learned residual models with like neural networks, where they just fly around, like these ones where they're doing the flying through the gates and trying to do really aggressive minimum time stuff. There, you really need super dialed models to do that. So they're basically taking pretty high fidelity models with like legit propeller models, legit aero models as a baseline. And then they're flying around a whole bunch. And then they're taking the residuals and fitting a neural network to the residuals and doing like an extra residual term to capture sort of even more aerodynamic effects that they're missing in the first principles models. So you can get really deep on this. So the guy who, I would say the group that's like farthest in this kind of area that's doing that residual modeling stuff, it's Davide Scaramuza's lab in Zurich, if anyone's heard of them. They've done like they've set all the records and like beat the best human drone pilots now at sort of racing around a track through gates. And that's kind of what they do. And they have a bunch of papers on this. Yeah, cool. So any questions about this before we go do it? Everyone cool? All right, so here we go. Here's the code. Kind of step through this and hopefully show you how it's done. So this is just LQR, but you know, like we said, this is like you can do all the same stuff we've been doing all along this way. So you can throw this into MPC super easily. You can throw it into, you know, kind of anything else you want. So this is all stuff we've seen before. Here's our sort of standard Quaternion functions. These LNR matrices, and then attitude Jacobian, and then we're going to choose to use sort of Rodriguez parameters or Gibbs vectors for our error state. You can use anything you want. It's also common to just take the vector part of the Quaternion from the error Quaternion, or use axis angles. Like you can pick anything you want there, and it doesn't matter. It turns out they're all equivalent up to a scalar factor. So there's maybe some factors of 2 floating around, but otherwise everything's the same, and it doesn't matter which one you choose. So that's what we're going to choose kind of arbitrarily. Here's our quadrotor model. I've just kind of made these up based on some like reasonable numbers for like a DJI drone or something. So it's like 0.5 kilogram. So the sort of, is that 17.5 centimeter L? So it's like about this big between the center mass and the prop, sort of roughly a drone about this big. Those inertia numbers, that's ML squared. That's about what these things are. And then these thrust and moment coefficients are sort of just made up and about order of magnitude about right for what you would see. So if you want to use this for something real, probably want to go get better numbers here, do some SysID or measure some stuff. But this is pretty much, you know, what you would see. And then we're going to do 20 hertz, just arbitrary again. Most of the control loops on drones, like standard hobby stuff you'll get are 50 hertz, which is just kind of because that's what most servos operate and stuff like that. So, you know, you can make this high if you want to. The nominal state vector with the quaternion in it is 13 dimensional. And then our sort of reduced state with the tildes are going to be 12 dimensional, right? 4 inputs, and we're just arbitrarily going to run this for 5 seconds in the sim and play around a little bit. Here's that big E matrix where we've basically just taken a block diagonal concatenation of identity stuff and then put the attitude Jacobian in the correct spot for the quaternion. That's easy. Here's the quadrotor dynamics we just wrote down. Nothing crazy. It's exactly what we just talked about. And then we're just to be extra careful, we're gonna normalize the quaternion on the way in to just mop up any integration error or whatever. I'm also gonna normalize it in the RK like we've done in the past. So that's all good. Here's the RK4 stuff like we've done, just regular RK4 step, and then we normalize the quaternion at the end of the RK4 step to make sure that stays correct. Then we're just gonna sort of randomly, so this is initial conditions, and in particular, we've got hovering in here. So this is just taking mg and dividing it by 4 and making the thrust from the props equal to that so that we're hovering. A meter off the ground, sort of identity attitude, right? One other thing to be careful of here, I'm assuming like a right-handed coordinate system on the drone with Z up, but the standard coordinate frame for airplanes actually has Z going down through the floor of the airplane because pitch, roll, yaw, it turns out. So be careful with this. You'll actually very often see upright is actually upside down from what you might think. So if you go use a lot of the simulators, that's a common like airplane convention because it makes the XY body coordinates line up with pitch and roll in like the right-handed sense. And then if you do right-hand rule, it ends up with yaw being aligned with Z through the floor. So be aware, like I'm doing it this way. You'll see this like this in a lot of drone applications, but a lot of aero stuff that comes from airplanes uses a different convention where Z points sort of what you would expect to be down. So just be careful. Okay, so here what we're going to do is usual forward diff of the nominal dynamics around that hover point. Yeah, Jeff? Yes, exactly. So this is the identity quaternion, right? Scalar part 1, vector part 0. So it's cos theta for the scalar part. The cos 0 is 1. So the axis angle corresponding to this would be 0. I'm not sure I follow. It's just zero. Like there's no, that's the identity quaternion, right? And that will map to a zero axis angle. If it were this opposite convention, like we are saying, where sort of positive Z is through the floor of the airplane or the drone, then this would actually be like 180 degrees to make it upright so that this works out. So that's just an FYI thing. Like you will see that if you do aero stuff, because that's a common convention. Okay, so we're going to linearize this and keep in mind, this is 13 dimensional, right? So if I look at A is 13 by 13, right? So for it, we're going to go check the rank of A, and it's rank 12, right? And similarly, if I go check the controllability matrix for this guy, again, for it to be controllable, we want this thing to have rank 13. If it's a 13 by 13 thing, rank 12. So I can't do LQR on this. Riccati will barf. Things will not work. And so we have to like do something a little extra. Okay, so we did that. So now we're going to go do this trick and do this reduced system thing. Now this thing is 12 by 12, right? So we can check that. Oh, I zoomed out. Now I can't see anything over here. I forgot to push the podium up. Very annoying. Can't see what I'm doing. Okay, so cool. So the A tilde is now this guy's, what the hell did I do? Okay, 12 by 12, cool. We're going to check it here, rank 12. So that checks out, right? So this thing is now, and controllability, blah, blah, blah. This is controllable, right? All good. Okay, so now we're going to do our usual LQR thing. I'm just making up cost weights, nothing fancy, right? Identity, blah, blah, blah. We're going to call DLQR, which works, obviously. If I tried it on the original A and B, it would barf and say it's uncontrollable. Yeah, that's right. Yeah.
Can you specify like what you care more?
Totally, yeah. So if you care more about like yaw, for instance, you would sort of put a heavier weight on that third component.
It's dependent on your.
So those things at the identity, like under small, for assuming small angles, they're all the same. That's sort of a subtlety that's, yeah. So like the tangent space is a vector space. And so kind of by that notion, like all you can really do there is sort of like linearly scale stuff. I mean, you could make one up that did, but that would be evil and terrible, and you would not do that. Oh no, like if you, yeah. So to be clear, right, all 3 parameter attitude representations have a singularity somewhere. You could, and so Euler angles have one at 90 degrees pitch. The sort of standard Rodriguez parameters and the axis angles have it at 180. And then the modified Rodriguez parameters have it 360, which is kind of really nice. And that's why those things are widely used in aerospace circles and people like them. So yeah, they all have singularity somewhere. You could invent one that was singular at 0. In fact, there is one that does. These are so-called shadow parameters for the modified Rodriguez parameters. The deal there is that has a singularity at 360, which is equivalent to the identity, right? So there's a so-called shadow set that flips it around and has the singularity at 0. The idea is when you're using these things online, you can write controllers that basically switch back and forth between the standard ones and the shadow ones when you get close to 360. So you can like sort of just have a sort of a hybrid controller that switches as you get close to the singularity. So that's an option. There's a whole literature on doing stuff like that. So you absolutely can. There are ones that do, but you typically want to avoid that. Also, if your error is 360 or close to 360, you're pretty screwed anyway, right? So that's kind of the gist is like what we just did here has a singularity at 180. If your error is 180, you're really screwed, right? And you're probably going to crash and die anyway. So I think that's sort of the hand wavy logic for why this is okay to do. And if your errors are really 180, something has gone very badly for you and you're probably in trouble anyway, regardless of what's going on here, right? Okay, so there's our K matrix. Here's the controller. It's again what we said. So we're going to compute. So we're going to split out some of this stuff. We're going to compute our error rotation. We're going to take this quaternion multiplication with the reference and then convert it to a Rodriguez parameter vector. That's what our choice of phi is here. And then we're just going to throw that all together in this delta x tilde thing, hit it with the K, and have the reference in there too, the hover reference. So that's the controller. Now we're going to go try this and do some sim stuff. Hopefully this doesn't take forever and barf at me. And let's see what happens. Oh yeah, I gotta do some. Okay, so we're gonna just try some stuff. Yeah, so that was like wildly off. So I'm sampling random initial conditions here with a pretty big covariance and just kind of letting this thing rip. So yeah, this is literally adding yeah, so I'm literally starting it like upside down here, which is pretty nuts, and it still works. The sort of, yeah, you can see these are like really aggressive attitudes. So in practice, what would happen here is you would probably hit your torque limits and saturate, and this might fail due to that. But if you went and put this into an MPC controller that could reason about the torque limits, as we saw with the planar case, it works super, super well. Like you can do really wild stuff with this really far away. Keep in mind, this is an LTI model linearized about hover, right? So it's all kinds of, it's a single model. There's nothing in there that's sort of nonlinear really. And I'm running this on the full nonlinear model. And it's doing really well with these really wildly off, initial conditions. Caveat, right? Like this will break because there's stuff missing from the model. So in particular, it'll break. Let's try this again. Yeah, so that's like sideways, right? And it's working really well. Reasons it'll break, torque limits, which you can handle with MPC. After that, it's going to probably break because if you're pushing this thing really hard, you're going to start hitting model errors due to missing aerodynamics terms and all the stuff we were talking about before about prop coefficients and things like that. So it will break, but this is extremely robust under any kind of normal flying conditions. Like you can basically be sideways and it's fine. So anything short of like wild aerobatics, this works really, really well. Okay, questions about anything? Want me to try anything crazy? Yeah.
When we were talking about like our reference trajectory, in this case, we don't even really have that. We're always just referenced around the origin, right? So like you could be like way off.
Yeah, this is literally linearized about hovering just sort of a meter off the ground. There's nothing else in there. That's it. Single LTI model. And if you basically play the Quaternion tricks right, and you do these body frame error state kind of tricks with the velocity in the body frame, et cetera, it's insanely robust to like really huge errors. So if you wanted to do wild aerobatic stuff, like what you do then is probably have a slightly more high fidelity model that captured some more of those aerodynamic terms. And then you run nonlinear trajectory optimization on that nonlinear model where you take a few Newton iterations. If you can do that fast enough, which often you can just straight up do that online and run nonlinear MPC. If you can't do it fast enough, you could do it offline where you optimize some crazy barrel roll thing. And then you would linearize around that barrel roll trajectory, get a linear time varying model, and then do time varying LQR to track it. And that would work really well too, right? And there, the errors have to be less than 180, but you can be upside down. And if the error is, around there, totally fine. And it works super, super well. Let me see if I can show you a cool video of this sort of thing. So this is, yeah. LQR is not going to do a bang bang thing, but where the bang bang thing would come in here is if you have really huge errors and you're running an MPC controller that can reason about the torque limits, it's probably going to slam you up to the torque limits, in some of that recovery maneuver, right? And then kind of get you back on the rails. So here's a fun video of exactly what I just showed you. This exact LTI model running on a crazy fly drone on board. This is from last ICRA from our lab. This is a paper called Tiny MPC where we developed an MPC solver that could run at like 200 hertz on an STM32 microcontroller. This is 90-degree initial attitude error, showing you we're just going to like kick it off this little platform and watch the MPC controller recover. That's it. Like really good. If you tried the same thing on the built-in controllers that come with the Crazy Fly, there's like 4 different ones. There's like a PD thing and a couple others, completely barfs because it doesn't, those sort of stock kind of linear controllers or even non-linear controllers can't reason about the actuator limits. So they saturate the actuators and the thing just freaks out and crashes. So yeah, that's it. That's working. It's what I just showed you kind of working on hardware at a couple hundred hertz. Yeah.
Take measurements to get all the experimental data we were talking about, like your moment of inertia?
Yeah. So I think actually we fudged a lot of that. Like obviously mass you can get on a scale super easily. I think we grabbed their inertia numbers, their stated inertia numbers from the Crazy Fly code or papers. We didn't actually measure it. We just grabbed the rough numbers from their CAD, I think, ultimately. And then yeah, I think all the prop coefficients that we grabbed from their code, like we didn't do our own SysID or characterization really. We just used the numbers that were floating around in their firmware or published elsewhere. And yeah, I mean, the other part of that story is that this stuff's really robust to like like it's an LTI model, right? The model's already kind of garbage. So it's not like super sensitive to parameter error. Like it works super, super well. And the story there is like feedback is kind of magic. Feedback is really helping you mop up all these errors, right? So yeah, convex MPC. This is just QPs at 200 hertz on a microcontroller, real time. We're doing it in mocap, so it's getting the mocap measurement streamed to it, and we're running a Kalman filter on board that's fusing the mocap with the IMU. But yeah, it's pretty vanilla stuff. And like, again, if you can do this stuff fast enough, you can kind of do pretty crazy stuff on hardware with it. Okay. I think that's all I've got for today.